Thank you. and without further ado, I would like to share a little bit about GraphLab. And as we're thinking about this conference and this event, which is a great time for us to learn from you, I thought one way of doing this is to give a retrospective of how we got here. It's been about 6 years that we've been in this project, and I thought it would be fun to talk about the road behind us and the road ahead of us. And as I thought about this, I ended up thinking about how technology evolves and how we have evolved in that context. And if I think about technology, you can often split the evolution of technology into phases, and I think about 3 key phases. First, there's the phase of possibility. Here's something that you couldn't do before that you can do now. And a great example for me is the horsey, horseless carriage. We're all riding around in chariots with horses and carriages with horses, and suddenly somebody invents a motor, and then they put it on a carriage, and it rides around by itself, but they're so overwhelmed by the experience that they decide to put a head of a horse in front of the carriage, just so it feels more comfortable. And the great thing about the age of possibility is that it's inspiring. Something that you couldn't do before is possible now, but the issue is that you have to be an expert to use these horseless carriages. You have to be a mechanic. And some time passes and technology evolves, and you get to what I think about as the second phase, which is the phase of scalability, where we take this technology and we push it to a degree that we couldn't push before. And in cars, the default example of this, of course, is the Ford Model T, where Henry Ford scaled up from 10,000 cars in his first year to about 10,000 cars a day 2 decades later. And what characterizes the phase of scalability is a lot of things, but in a very rigid way. So that's well characterized by Henry Ford's famous phrase, any customer can have a car painted in any color they want, as long as it's black. But people are not so happy with black cars. So after some time comes what I think about as the age of usability. And since I'm not just happy with a Model T, I want more than a car, I want a Cadillac. And I want great amenities associated with it, like a windshield wiper. And things that help me use this technology, like gas stations everywhere. And then things that make my life easier, like an automatic transmission, or safer, like an ABS brake. And so, as I was thinking about the history of GraphLab and the history of technology, I was thinking about these phases. First, possibility, then scalability, and finally usability. And if we get to usability, we can get to wide adoption beyond the set of experts and enthusiasts that could use the original technology. And GraphLab itself was inspired by machine learning, because we were working on machine learning for several years in my lab when I was at Carnegie Mellon. And we can step back and think about the phases of possibility in machine learning. And this is a great example that I love. It's a Rosenblatt perceptron. And this is a great device. So the box that you see on your right is a camera that has 20 by 20 pixels. And he would show it images like triangles, circles, and squares. And as it saw his images, it moved little motors on the left and learned to classify new images. So soon he could give it new images, and we could figure out if this was a triangle, a circle, or a square. And this is possibility. Nobody could make a machine learn. And suddenly, he could make the machine learn just by itself. But that's just one example, and possibility evolves over time. And another great example is if you flash back to 1998, where Yahoo had this great idea. Let's take every web page and just classify by an expert. This is about sports, it's about football, it's about Brazil winning the Confederates Cup yesterday. And if we do this right, all a user has to do is click a few links and find exactly what they want. And then Google came along and said, forget that. There's too many web pages. Why don't we just learn a mapping from queries to what people like, what people are interested in? And that's where machine learning shows another phase of possibility. But if we think about most of machine learning today, we're really focused on scalability. And this has been the core of GraphLab for the last 6 years. How do we scale up these ideas? And needless to say, we're thinking about this in the context of big data, be it the billions of images in Flickr or the 72 hours of YouTube video uploaded every minute, which nobody watches. And this became such a big buzzword that last year there was this great New York Times article where it said, data is a new economic asset, like currency or gold. which I find kind of funny. Because it's not an asset until you extract some value from that data. And being biased as I am, we need to think about how to extract that value. We think about machine learning. And the question here is, how do we design these algorithms at very large scale in parallel systems? And a default system that you might want to use, of course, is MapReduce, which is implemented in the open source system Hadoop, where if I have billions of, say, YouTube images, and I want to extract faces and figure out if that person is hot or not, I can just send them independently to different processors, make little classifications, and then aggregate the answers. So Hadoop is good for solving lots of independent sub-problems. And it's the big elephant in the room that we need to talk about. But from my perspective, it's more like a white elephant. And if you look it up on Wikipedia, it's something whose cost of upkeep is perhaps out of proportion of its usefulness today. And we're not the only ones saying this. There's lots of people thinking about the limitations of existing technology. And so the question is what to do next. And that was the question that we posed when we started the project. And we realized that data parallel problems that can be well expressed in MapReduce are good for things like extracting faces independently in each image. But there's more to machine learning. There's more that doesn't fit that mold. And so here is a cartoon example of that. If I show you this little patch from a bigger image, I might ask you what it is. Might be hard to tell. But if I tell you it's near this other patch, maybe that helps. But if I step back and look at the big picture, you're thinking World Cup 2014. So the value in the data is about dependencies. And the question is, how do we represent these dependencies in a way that lets you scale up to big problems? So another flashback to 1998, where I don't know if any of my Yahoo friends are here, but I didn't use Yahoo. I used this other little search engine called Alta Vista. And a little company came by and somehow made me switch. And the question was, what was the technological transition about? What was new? And arguably, you could say that the new thing that they had from a technological perspective was a graph algorithm called PageRank and a system to scale up that computation to really big graphs. And so our belief is that the next phase for us, this next phase for technology is thinking about graph data, structured data in this way. And graph data is not just about social media, but it's also about relationships between things in science, advertising, the web, and beyond. Because it captures relationships between people, products they buy, ideas that they have, things that they share, and beyond. And the graphs that people have been using GraphLab for these days have hundreds of billions of vertices and edges with lots of rich metadata. So just to give you an example of how graphs go beyond just a social network graph, you can look at Facebook graph, and you'll notice that, of course, there's a friend relation that connects together people, but there are other relationships. For example, pages that you liked, or articles that you posted, or things that you shared. And so this set of relationships form a graph with lots of metadata and lots of annotations. And the question is, how do we do machine learning on this type of data? So let me show you a few examples. They're cartoon examples of machine learning algorithms. So let's say that I have a large database of images, and I label this face as being my grandmother's face. And I want to propagate that through the database of images, and I realize there's this new one whose similarity is not good enough to make a strong prediction. What can I do about this? Well, what I can do is connect faces together in graphs. So I can look at other images in my database and look at ones who have similar faces, connect those together, and then use other information. For example, people from the same family tend to co-occur together in different images. So if I add those co-occurrence edges, maybe I can make even better predictions. By propagating information through this graph and being able to say this picture is of my grandmother. And so for those machine learning geeks like me, the type of ideas I'm thinking about here are called probabilistic graphical models. So that's one example of graphs that you might derive from data. But perhaps about half of our users today of GraphLab use it to build recommender systems. And this is a well-studied problem where the graph is between people and products that they like or things that they're interested in. So for example, let's take this user whose favorite movie is Women on the Verge of a Nervous Breakdown. Great movie. He also likes The Celebration, City of God, and Wild Strawberries. What other movies would you recommend to this user? It might be a little hard to tell, but thankfully there are other users like him who have liked similar movies and have also liked movies such as La Dolce Vita, so perhaps La Dolce Vita is a good recommendation here. So here you see a graph that connects people and movies. And the type of algorithms that we use here are called latent factor models or non-negative matrix factorization. So let me show you one more cartoon example here. So let's say that I have a large social network and I want to figure out how to advertise to different people. One way of thinking about this is by looking at their political bias. So I can label some people's posts as being liberal and others as being conservative in order to make predictions about people's political leanings. And you can use that classifier to go around the social network and classify different people's basis on their interests. But the problem is that most people in the social network are kind of like me. They don't post anything. And so the question is, what do you do? Thankfully, we have a graph, a social graph, and you can connect people together in a social graph, and we can propagate information from people that we know to those that we don't know much about. And this propagation allows you to make better predictions, and the type of algorithms you might do here are things like semi-supervised learning or transductive learning. And finally, in a lot of advertising problems, you want to do text analysis to understand what particular items are about, for example, books. And what you can do is build a graph that connects, say, books and words that appear in those books. And using some unsupervised learning techniques, you can automatically discover that in these books, there's some topics about apples, there's some topics about computers, and especially if this was YouTube, there's a big topic about cats. And so the type of models that you can use here are things like latent Dirichlet allocation and others, so LDA. So in general, the idea here is that you start from some data, be it images or documents, you extract some features, let's say faces, and connect them together in a graph of relationships, and you do this magical structural machine learning algorithm that somehow is supposed to extract some value from data. And so since this process is challenging, time-consuming, the goal of Graph Lab is to shortcut this and enable you to do it much faster, end-to-end. So that was a goal, and what we wanted to tackle was the types of algorithms that don't fit well into the data parallel problem. They fit more into what we call graph parallel problems. So things like graphical models, supervised learning, collaborative filtering, graph analytics, and beyond. So what we're going to do in the rest of the talk is talk a little bit about how Graph Lab does this, and what does it mean to program for these types of algorithms. And I'm going to use a simple graph parallel algorithm example, the one I mentioned earlier from Google, the PageRank algorithm, which you could use, for example, to find out what the social rank of this user is. So I want to figure out what her rank is, and I don't know it, but what PageRank says, it depends on the rank of the users who follow her. And what is their rank? I don't know, but it depends on the rank of the users who follow them. And so since this graph has cycles, you have to somehow iterate something until convergence. And what PageRank does, it iterates a simple formula that says, my rank is the weighted average of my neighbor's ranks. My rank is the weighted average of my neighbor's ranks. And it does this again and again and again, and eventually it comes up with a rank for web pages or for a social network. And it's a good example of a graph algorithm because you start from some graph dependencies in the data. You do some local updates, some local transformations. Let's say my rank is the weighted average of my neighbor's ranks. And you iterate this again and again and again until convergence. And it turns out that the algorithms that I mentioned, the problems that I mentioned that don't fit so well into MapReduce, they fit well into a graph parallel abstraction. So an abstraction allows you to write this type of algorithm. And when you're building this, one of the fundamental questions that comes up is one of synchronous versus asynchronous computation. So if you go back to the bulk synchronous parallel model of Valiant from about 2 decades ago, which is implemented in Prego and also in Giraffe, what he said was something very simple. Imagine attaching a processor to each vertex in the graph. You do some thinking independently. It's like everybody in this room here did some thinking without talking to anybody else. Once you're done thinking, you talk to all your neighbors, you hit a barrier, and then you iterate. It seems like a very natural way to think about this graph algorithms, But it turns out to be highly inefficient. In fact, it's provably inefficient for very large problems in machine learning. So here's a cartoon example of that. So I'm taking the image on the top left, which is a noisy image, and I'm connecting neighboring pixels in a graph, and I'm going to use a standard algorithm to try to remove that noise. And what you realize is that the areas in the boundaries are the ones that are hard to make a decision. And so if you use an adaptive dynamic algorithm, what you get is something where in the beginning you do computation everywhere, but soon you discover that there's some harder parts of the problem, and you focus your computation on those hard parts. And you see here that most of the computation is happening around the boundaries in the image. And so an algorithm that is asynchronous is able to identify those problems and is able to get much better performance. And this was the beginning of the GraphLab project, thinking about this asynchronous algorithms. And when we got to that point and started doing experiments, we realized that this was a practical and theoretical issue. So in the x-axis, I'm showing you a number of processors as we scale up. On the y-axis, running time. If you use a synchronous algorithm, you get perfect scaling. But you're scaling up a really slow thing. In fact, an asynchronous algorithm with one processor is faster than a synchronous algorithm with 8 processors. And this is not just an empirical validation, but it's also a theorem, which I'm not going to get into today. So this was about 6 years ago that we started this type of analysis, and we're feeling pretty good about ourselves until we started implementing these algorithms. And the truth is that it was painful. It was painful for my students, actually, who were sitting here, not for me. It was a totally painless process. And so it was so annoying that we decided to build a little system for our lab so we could implement this kind of algorithms at scale. We called that system GraphLab. And we realized that GraphLab will help us write algorithms for solving these machine learning problems. And the goals in the beginning were ones where we knew how to solve a machine learning problem on one machine using MATLAB. Somehow we wanted to hand it to GraphLab and on, say, Amazon Cloud and automatically get parallel predictions and write lots and lots of papers. So for us, that was possibility. That was saying, here's something that we want to do that we couldn't do before at scale. So what I'll tell you about first is that first version of GraphLab, where we started by formalizing the idea of these graph programs with graph-represented data, let's say a graph in a social network, where every vertex associated with some data, for example, uses profile, and every edge is associated with some data, let's say similarity weights between users. And you want to do some computation on this graph and compute some stuff. And the question is, how do you compute stuff in a graph? You do it by thinking like a vertex. And the question is, how does a vertex think? It thinks by looking at itself and its neighboring vertexes and edges. And so let's go back to PageRank. So how do I think? I look at my neighbors' ranks currently, then I recompute myself as the weighted average of my neighbors' ranks, and if my answer has changed enough, I go back and I tell my neighbors that they need to recompute their value. And this is an example of dynamic computation. And so what GraphLab 1 allowed us to do is to do this kind of computation very easily. You wrote this update functions, and they get automatically parallelized for you, scheduled and prioritized in all sorts of different ways. And one of the issues that came up in the process, which, being kind of theorists and machine learning guys, we weren't thinking about this too much, was the idea of race conditions. Race conditions. So the issue here was that if the red vertices are operating parallel, and you start executing the blue vertex, they might modify data on neighboring nodes at the same time. And then you can end up with a race condition. And as we got to that point, lots of people told me, oh, this is machine learning algorithms. They're all statistical. Who cares about race conditions? You should just run and hope for the best. So what they're saying is that if you don't have consistency, you can have higher throughput, more updates per second. That's always true. But for some algorithms, it's good. And for some other algorithms, you can have potentially slower conversions or even diversions. So this is being able to turn off consistency, it's an algorithm-specific, problem-specific issue. So for example, if you take movie recommendations on Netflix data with just 8 cores, and in the x-axis I'm showing updates over time, on the y-axis error, In this particular case, if you don't guarantee consistent updates, this is the kind of behavior that you get. It oscillates a lot. If you guarantee consistent updates, this is the kind of behavior that you get. Quickly converges to the right answer. So what GraphLab allowed you to do, GraphLab 1, is turn consistency on and off depending on how confident you were about your algorithm. So this was the way we thought about this when we started, a graph representing data, a update function like my rank is the whatever name was ranks, and a way to schedule this in a distributed way, and consistency models that were user defined. And we put this out in the open source community almost as an afterthought. We were just interested in writing papers, but somehow it got picked up, and lots of people wrote all sorts of algorithms on top of GraphLab. And they were getting really interesting performance. So for example, this is some results on a project from Tom Mitchell's group at Carnegie Mellon, or something called the co-EM algorithm. And they want to scale this up to some pretty big problems, and they couldn't solve it on one machine, so they tried Hadoop, and they could now solve it. With 95 cores, it took them about 7 hours. This is possibility. But 7 hours can get long, and they tried GraphLab, and with 32 C2 machines, it took about 80 seconds. So this was about 0.3% of Hadoop time. So stepping back and thinking about the first version of GraphLab, what we realized is that many machine learning algorithms can be written as these vertex programs, and asynchronous executions and consistency models are fundamental to think about these algorithms. And we're feeling a little too good about ourselves at that point, I would say. And we said, what is the biggest graph that we can download in the open source kind of domain, public domain, to try out and show off to our academic friends? And this was a graph of about 1.4 billion vertices and 6.7 billion edges, which seems pretty small today. The Alta Vista web graph from 2002. And GraphLab 1 just did not scale. It did not do well. You might as well have used Hadoop at the time. And so, being defeated, we decided to step back and see what the issue was. What was the problem? And the problem is that this was a natural graph. A graph that results from a naturally evolving phenomena, like a social network. And natural graphs have interesting properties where existing distributed systems have terrible performance issues. And the problem is that GraphLab 1, Prego, high-performance computing systems typically assume that graphs are relatively uniform with small degree vertices. They're relatively easy to partition among machines. But natural graphs are nothing like that. They have this very high degree vertices that follow a power law degree distribution, and they're very hard to partition across machines. So let's talk about high degree vertices for a second. If you take the web graph, what I'm showing in the x-axis is the degree of a vertex, on the y-axis, the number of vertices of that degree. So on the rightmost, you have Google. Somewhere in the middle there, you have, let's say, Alta Vista. And then from the far left, you have Carlos Guestrin. And the top 1% of the vertices are associated with about 50% of the edges. So that's very high degree. And this is not just an issue in the web graph. If you take a social network graph, you can have very popular people that are connected to many, many others in the social network. If you take a movie recommendation system, you can have a popular movie that many people watched, so it's connected to many people. If you take a machine learning problem, you have something called a hyperparameter, which is connected to many of the vertices or all of the vertices in the graph. And in text analysis problems, you can have a popular word that appears in many, many documents. And so what this leads to is star-like motifs in graphs, where you have, let's say, a popular person with many followers. And this can be really bad for distributed systems. And the reason here is that most existing systems, they partition vertices among machines. Imagine you have a social graph and you're partitioning users across machines. It's a very natural thing to do, and you end up cutting edges, relationships between users, and the amount of communication that you have to do is linear in the number of edges cut. And the problem is that even if you could solve the NP-hard graph cutting problem, in natural graphs there's no cheap edge cut. And existing distributed systems and graph cutting systems like Metis don't scale up to these big graphs. And so because of these issues, GraphLab 1, Prego, and systems built by folks like Twitter, Facebook, and others use what's called hash partitioning, which is a fancy word to say they randomly assign people to machines. And proof by PowerPoint, you cut a lot of edges. So here's my only equation for this talk. In fact, you can easily prove that if you have P machines, you're going to cut 1 minus 1 over P edges. So if you have 10 machines, you're going to cut 90% of the edges. If you have 100 machines, you're going to cut 99% of the edges. And so you might as well use MapReduce. There's no advantage of having that graph structure explicit. So that was our wall. We understood our wall. We understood the issue that GraphLab and Prego were having in these natural graphs, this poor performance due to bad partitioning. And that led us to develop GraphLab 2, which was codenamed PowerGraph. And the focus there was scalability. So if GraphLab 1 was about possibility, GraphLab 2 is about scalability. So start thinking about what GraphLab 3 is about. And so the notion here was, if you step back and look at these machine learning problems, like PageRank, for example, they typically split into phases. First, I gather information about my neighbors. What is the current rank? Then I use it to change my own value. My rank is the weighted average of my neighbors' ranks. And then I signal my neighbors and tell them to recompute something in what we call a scatter phase. So that means a computation can be broken down into a data parallel MapReduce style computation over my neighbors, which we call the gather phase, which is then leads to a local application of that value, and then leads to a data parallel scattering of information about my neighbors. And this led to the gather apply scatter model of GraphLab 2, which we call the GAS decomposition. We're terrible at acronyms. And it turns out that many machine learning algorithms fit into the GAS model. So graph analytics, inference and graphical models, matrix factorization, collaborative filtering, clustering, LDA, and many others. And one of the key insights here is that when you use the the GAS model, what you end up doing is not assigning vertices to machine and cutting edges, but you're assigning edges to machine and cutting vertices. So vertices get replicated among machines. And communication now is linear in the number of machines a vertex lives in, and this is called the vertex cut problem. And percolation theory suggests that it's possible to have a low-cost vertex cut even for natural graphs. And so what GraphLab 2 did is come up with some streaming graph cutting algorithms for vertex cuts that scaled up to really big graphs and provided an order of magnitude performance gain. So if we show you some early results from GraphLab 2, what we're showing here is the Twitter graph from 2010 for about 40 million users and 1.4 billion edges. And we're running PageRank on this graph. On the left side, I'm showing communication, right side running time. And we see the GraphLab 1 had to do a lot of communication, which led to a long running time. If you implemented Prego and Piccolo, you had reduced communication, which led to a reduced running time. But with PowerGraph, GraphLab 2, we could reduce communication much further and provide an order of magnitude reduction in the running time. And this was the big gain with a second version of GraphLab. And the second version was a much more robust, scalable system. It wasn't just about abstraction. It wasn't just about writing papers. We started to notice that we had a community, and we started to support the community. And we launched this a year ago at the workshop here. And it was built on standard cloud infrastructure, and we had a bunch of boxes that did things like graph computation as well as MapReduce and some other things you might need. And it was abstracted away in the GraphLab API in C++. And on top of it, there's a bunch of toolboxes for doing things like graph analytics, collaborative filtering, graphical models, clustering, text analysis, and computer vision that were written on top of that API. And if we talk to our users, to GraphLab users, I would say initially, most people use GraphLab because they were interested in these algorithms for machine learning that scaled up to big problems. So most people just program directly by using these APIs, so these toolboxes. And it was great. Some people were writing their own toolkits, and we're announcing today a few toolkits written by other groups, and a few of you were brave enough to hack into the GraphLab source code itself. And it was exciting. It's been very exciting last year. And just to give you a sense of the scalability of GraphLab 2, which is what we focused on, if you take that Twitter graph from 2010 with about 1.4 billion edges, there's a standard task in social networking to figure out who are highly influential, popular people, which is called triangle counting. So somebody who's part of many three-way relationships, I'm friends with Mary, Mary is friends with Bob, Bob's friends with me, tend to be really great people to advertise to. And this is an important problem where there was a paper in 2011 where they used Hadoop to solve this problem. With about 1,000 machines, it takes them about 400 minutes. Which was a possibility, but with GraphLab 2 and 64 machines, it takes about 15 seconds. And this is not just because Hadoop is in Java and GraphLab is in C++, or even because GraphLab keeps a lot of stuff in memory and Hadoop uses disk a lot, but it's because if the graph is explicit, you can do much better computationally, even asymptotically. So Hadoop is, or MapReduce is just the wrong abstraction for this problem, requiring degree squared communication, which can be very costly. So it's a power of abstractions here. Now, faster running time is just one model or one measure of value. Another measure is programmer time. So let's take a text analysis problem that I mentioned earlier called topic modeling. LDA is an example of an algorithm of that. And this is very important in advertising. I want to find out what web page is about in order to figure out what ads to place on that web page. And this is such an important problem that Yahoo built a system just to solve this task. It's an awesome system that Alex Mola built. And at the time, he could process about 150 million tokens per second, which is a very impressive rate. With GraphLab 2, and that was with 100 machines. With GraphLab 2 and 64 machines, we could process about 110 million tokens per second. The difference is that the Yahoo system was built just for this task, while GraphLab, it took my student, Joey, about 200 lines of code and 4 hours to implement this algorithm. And this hints towards where I want to go, which is make most of your time and allow you to scale to problems that are much bigger than you could before, without having to build a system dedicated to that problem. Now, if I step back and look at the problem that was stomping us, this was the graph that now feels small with 1.4 billion vertices and 6.7 billion edges, the AltaVista Web graph from 2002. We can now run it, let's say, on 64 EC2 machines, about 1,000 cores, 4 terabytes of RAM, and it takes us 7 seconds to iterate over the graph. So that's about 1 billion links processed per second, and it's only 30 lines of code that we had to write. And so at that point, we're feeling pretty good about ourselves. And another one of my students, Apo Kirola, walks into my office and says, "Buy me a Mac Mini." And I think he wants to watch TV. But he says, "No, I want to solve web scale problems on any computer." So there's a genesis story for things which may or may not be true. There's one for names which may or may not be true. And the name GraphLab, there's a lot of animal mascots out there. And I had a Labrador at the time, so GraphLab from Labrador. Apple wanted to build a small version of it, so he called it Graph Chi for Graph Chihuahua. And what he said was, I'm going to use SSDs or hard drives to solve these big problems efficiently. And the problem is, if you start using hard drives or SSDs, you end up with the issues of random accesses, which can be tremendously problematic. So if one piece of the graph is one part of the disk, and another vertex of the graph is in a different part of the disk, you spend all your time doing random seeks, and you don't get anything done. And what he developed was a new method called the parallel sliding windows method that minimizes the number of random accesses. So it's a little bit of advertising. Apo's going to give an overview talk on our project, I think this afternoon. But just give you a sense of the performance. If you go back to the triangle counting problem with about 1,000 Hadoop machines, takes about 400 minutes. GraphLab 2, 64 machines, takes about 15 seconds. Apo can solve this on a Mac Mini in only 59 minutes. So GraphLab 1 was about possibility. It was about figuring out that machine learning algorithms could be written as these vertex programs and that asynchronous execution and consistency models are fundamental. Well, GraphLab 2, Power Graph, was about noticing that natural graphs were the key challenge for graph computation in distributed systems. And now they're all the rage, actually. And that vertex cuts and the gas model were fundamental to getting a problem to scale to really, really big problems. So getting a system to scale to really, really big problems. But let's talk about where we're going with this. So GraphLab 2 was about scalability. And to be honest, it was at a loss of usability. In other words, GraphLab 2 was available in any color as long as it was black. And just to give you a sense of this, if you look at a GraphLab 1 program for PageRank, it's very intuitive. You say, compute the weighted average of the neighbors, and you reassign it to yourself. The program is exactly what you expect it to be. You can read it and understand it, and the code is intuitive. That's what happened with GraphLab 1. With GraphLab 2 and the gas model, this is the code on the right. It's short, and that's the most I can say for it. It's not intuitive. There is some implicit aggregation going on in this code that you have to understand in order to understand what's happening. Don't try to understand it. And you really have to understand how the engine works, what are the phases of computation in a new way in order to think about what that program does. And that was an issue. It was an issue here of accessibility. Who could use GraphLab 2? So GraphLab 1 provided great flexibility at the cost of scalability. While GraphLab 2 provided amazing scalability at the cost of usability. It's very handcuffing to that gas model. And implementing things like restricted Boltzmann machines, for those familiar with it, in GraphLab 2 was just annoying. It's an annoying pain. I think Danny did it, and Danny's here. So it's doable. But the question is, what should we do now? How can we do something in between? And what we really want is a Cadillac. That's what I want. But it has to be electric, by the way. And so what GraphLab 3, codenamed Warp Graph, does is hopefully provide more of that usability again. Because it allows you to program like GraphLab 1 by thinking like a vertex, writing these little vertex programs. But it gets executed like GraphLab 2 in this vertex partitioning way. So let me spend a couple of minutes telling you where GraphLab is going, what GraphLab 3 is about. And what we've noticed is that what we can do is expose fine-grained, highly parallelizable iterators inside these update functions. So if you take the PageRank equation, which basically says, my rank is the weighted average of my neighbor's ranks, if you write that as a code, what we're doing is updating my value to be some aggregate, some weighted average of my neighbors. So why not write that as a standard iterator that we're familiar with, for example, MapReduce over neighbors, if I'm just computing an average. So here's a program that you could write that's quite intuitive, update my value to be the weighted average of my neighbor's values. I can read it, I can understand what's happening. And what GraphLab 3 is doing, and actually the version 2.2 now is doing, is exposing this highly parallelizable neighborhood iterator. So for example, we can have a MapReduce over neighbors, which represents the gather operation. You can have a parallel transform over edges that allows you to do something like the scatter operation. And you can have a broadcast function that allows you to do things like scheduling over neighbors. Well, we have mood lighting now. Watch that hand. And so, in addition to this, GraphLab now unifies our model with what's called a parameter server, for those familiar with it, which is basically a distributed hash table where you can have global variables, where you can read and write keys beyond what's in the graph. So this is how we think about computation now, these parallelizable local iterators and this global distributed abstraction. Okay, we don't have mood lighting anymore. I have a headache. So GraphLab 2 is just extremely more expressive. It allows you to represent more easily any GraphLab 2 program, but it can do more. So you can do a sequence of multiple gathers rather than just gas model. You can do a scatter before a gather. So if a gather applies scatter was a gas model, you can think about what this is, the SAG model. And you can even do conditional execution. So for example, you say if some condition, do something, if some other condition, do something else. And so it's a lot more flexible. But the problem here is that the gas model allowed us to scale up to really big problems because we knew how computation was going to happen. It was going to happen in the scatter phase, in the supply phase, in the scatter phase. It was very repeatable and very predictable. GraphLab 3, because it has conditionals and everything else, you can't really tell what's going to happen. You could do a scatter gather, transform gather. And once you have unpredictable computation, the risk is high latency. And so you can spend all your time waiting for a reply. So the analogy here is, you ask somebody on a date, and you just sit by the phone all the time waiting for that person to call back. And so you need a way to hide that latency, and the best way that we know is to do something else while you wait. And so what we're going to do is create thousands of user threads that allows us to do many things while we wait. And this is in the spirit with the Grappa talk that we're going to hear from Mark today, I think this morning. But the problem here is that this can be a significant performance bottleneck because you can spend a lot of time context switching. In fact, the OS requires tens to hundreds of thousands of cycles to do context switching, and this can be extremely problematic. And so what GraphLab 3 does is provide a novel user threading that allows you to do about 8 million context switches per second on a machine, which is about 100 times faster than the OS. So that's why we can use those simpler to write, easier programs. And just to give you a sense of scaling, if you look at the PageRank algorithm, in GraphLab 2, as you increase the number of machines, you get some nice performance scaling. In GraphLab 3, you get, at worst, about 25% slower performance. So you get a little bit of a hit, but with much easier to program abstraction. However, let me note that this is a problem. PageRank on this graph is a problem where asynchrony is not so fundamental. In a problem where asynchrony is much more fundamental, for example, if you run graph coloring on this graph, things get better for GraphLab 3. So if you look at GraphLab 2 on this problem, it takes about 227 seconds, while GraphLab 3 takes about 89 seconds, so it's about 2.5 times faster. So we can have a simpler to program model that can be faster in some problems. And that's when asynchrony is fundamental. Okay, so GraphLab 1 was about possibility. So machine learning algorithms practice vertex programs, asynchronous computation, consistency models. GraphLab 2 is about scalability, so noticing the natural graphs were a key part of our computation in graph problems. And we dealt with vertex cuts in the gather apply scatter model. GraphLab 3 is focusing on usability. And our programming model allows you to access your neighbors through these highly parallelizable iterators. And there's some key latency hiding schemas to make that possible. And since I said GraphLab 3 is about usability, let me tell you that the consensus among GraphLab 3 users or the Warp Graph Engine users is that it's much easier to use than GraphLab 2. And this is for a user study group of 2. Those are beta testers, but I'm proud and excited to tell you that we're releasing GraphLab 2.2 today, which includes the Warp Graph Engine with much easier to program abstraction. And now we expect to get a lot more feedback in 2. And we're excited to get your feedback and see what works for you and what it doesn't. And one exciting thing that I'm not talking too much about here, but is that GraphLab 2.2 now supports streaming or dynamic graphs. So unlike all the previous versions of GraphLab, now the structure of your graph can change over time. Was that excitement, or was it just here? Exciting, good. So it's a big deal for us. It's very exciting. and it's something that I think will make a big difference for many of you. So consensus is that GraphLab 3 is much easier to use, but easier for whom? So I thought GraphLab was extremely easy to use. Anybody in my lab could use it. Now, we're seeing that GraphLab is useful for anyone in this hall. But I want to go beyond that. I want to make GraphLab useful for any data scientist. Or even beyond that, for anybody who is smart and has big data. And the question is, how do we make that possible? How can we do that in a very, very significant way? That's where we're going. This is what you should expect to see from us. And the new abstraction simplifies writing GraphLab programs, but you still need to get a cluster, install GraphLab, configure a system, write some C++ code, and do all sorts of things that are annoying. And I've always wanted to resolve these issues, but there was always a big barrier for me, which was I couldn't give my students PhDs for solving those problems. Hadoop integration does not get you a PhD, unfortunately. Just as an example. And because of that, and because of the great engagement of our community, we have decided that the project has reached a certain level of maturity that led us to spin it out of the university. So we're excited to now have, in addition to graphlab.org, we have graphlab.com. And we've been lucky to be funded by some great investors, Madrona and NEA and others. And our focus is on making GraphLab more usable and continue to support our community. So we're going to continue to have an open source project that evolves over time, but with increased support and increased usability. And just to give you a hint of this, so nobody's seen this before, but what we're doing is making it easier to do everything that you might want to do with GraphLab, including even kicking the tires of GraphLab. So right now, kicking the tires of GraphLab is hard. You have to install a system and get your data and do all sorts of things. For the upcoming release of GraphLab 3, you'll see that you can actually go into graphlab.com, log in, select a set of EC2 machines you want to use, or run in your own cluster, of course. You get a little link, and that gives you a Python console that allows you to interact with GraphLab on the cloud. And this is extremely exciting for us. So exciting, and I'm feeling so brave that I'm going to give you a demo of that. Okay. So here we are. Here's the GraphLab Python console, and we're going to start by importing GraphLab. So just like you'd import anything else in Python, and I'm going to read a data file, and this is going to be a graph. Does it say date? No, it should say data. Demo. This is the, sorry, data demo live journal. I hope I got this right. Oh, and I'm missing an extra slash. See, my typing ain't so great. So this is the live journal for those remembering the olden days of blogging. This is live journal graph, and I'm going to be reading it into GraphLab. So GraphLab, I'm going to start a new graph. Ooh. Autocomplete is good. This is one of the usability features. And so what I'm doing, GraphLab, so you see that I've typed, oh, sorry, live demo. I was ahead of myself. So I'm reading that input file, and what this does is loads the graph. We're using, I think, 31 EC2 machines here that we're able to acquire this morning, and I'm reading the graph in a distributed way into the EC2 machines, and this graph has about 4.8 million vertices and 68 million edges. So it's a relatively kind of medium-sized graph, not a huge graph. And as that graph reads, what I'm going to do is that first standard task, which is going to be triangle counting on this graph. So we're going to read the graph, and then we're going to do some triangle counting. If we read the graph. Okay. Well, I'm going to keep typing here and hope that this works. Rajat, where's my friend? Team member. I have lost an EC2 instance. Okay, should I just start the dashboard again?
Give me a minute to recover the EC2 instance.
Okay.
Okay, try again.
Try again, from the beginning?
From the graph equals, from instantiating the graph.
Okay, we instantiate in the graph. Pretend that nothing happened. Wait, did I redo that? Okay. No? Okay, apparently not. Okay.
Come to our table, you can watch the demo.
let me try again. Should I try again?
Yeah.
Otherwise, I'll show you a video of the demo. So TSV equals /data demo Okay, should I try? Yes, no? Oh! Woohoo! That looks promising. Let's not clap until it's done. Okay, so supposedly we're loading. Yeah, there it is. No hiccups. So EC2 is with us, and what I'm going to do is that simple triangle counting on this graph. And I'm going to capture the results back into, so I'm going to capture the results back into Python. Cute. So what we see here is that in a distributed way, I think on 32 EC2 machines, unless one of them died again, it takes about 5 seconds to count the triangles. And now we're processing the results and reading the results back into Python using a standard NumPy array. And you can choose whatever you want to use. And now I'm going to cheat and try to do some computations on this. I'm not cheating yet. I'm going to use copy and paste in a minute. But first, let me try to figure out what we've done. So let's see how many triangles we counted. So I'm going to use some standard NumPy functions. So I'm going to take my output. I'm going to sum it over. And you have to do this. NumPy stack. So you can see that it's actually Python code. So colon 1. So unless I mistyped something, nope. Sorry, one parenthesis missing. Print NumPy. Okay, let me be less brave and just copy some stuff from here, since we're running a little short. Okay, so now we've counted, and it's so in that process we counted about 400 million triangles, 411 million triangles, and since the data is back into Python, what we can do is do any kinds of things you might want to do in Python. So for example, let's build a histogram of this data. So just using standard things to build a histogram. And what you should see here, on the x-axis is the number of triangles, and the y-axis is the number of people that have this many triangles. And you can see there's some people over here who are part of, say, ones to tens of triangles, and this is a lot of people. This is hundreds of thousands of people, and there's a few lucky ones who are ones to tens of people who are part of tens of thousands of triangles. So, and since the graph is loaded to GraphLab, one great thing about GraphLab 3 is that you can do multiple types of computations on the same graph without restarting GraphLab. So this is one thing that was quite different from the previous version. So as a demo, I'm going to run PageRank on the same graph without doing anything else. We're just calling it on the same graph that we had before. So it's still loaded into GraphLab, so I just call it do PageRank on this graph. And I'm just going to call execute. And now we're going to be executing PageRank on all of the nodes, and it takes about 4 seconds, and we're reading the data back into Python. And here's where I'm going to cheat, and I'm going to copy the plotting code. Oh, I forgot to, since this is a demo, I forgot to tell it to store in anything, so I actually printed out hundreds of millions of PageRanks right here. So let me just type PR underscore results is equal to this. Okay. So now we're going to redo it, and after we redo it, I'm going to do some plotting. It took 5.9 seconds this time, and it's processing the results back into Python. And here's a histogram, and you can see most people have a very low rank, let's say rank around between 0 and 1, and there's some lucky few here that have high rank, about 6 to 8. And that's what we expect from a parallel graph. So this is a nice thing. So the graph is loaded into memory, and you can do multiple types of computations on the same graph. But I want to show you, since somebody rubbed their hands in excitement, I want to show you how we can do dynamic graphs. So we can load a graph dynamically over time, and the graph can change. So the example I'm going to give you is the LDA example. So this is topic modeling, and we're using Wikipedia data. So this is about 6 gigabytes, if you zip it together, of Wikipedia data being read. And what you see here is we're loading all pages that have the word pi in it. We're geeky. I'm sorry. And what we're going to do is run LDA, which is a standard text analysis problem. And so I'm going to copy the code in here so we can go a little faster. And so now it added about, about 4,000 documents in Wikipedia that have the word pi associated with it. And we started. And LDA is going to be an anytime algorithm. So GraphLab is running the background, computing these topics on the data, and at any time we can ask it, what are the current topics associated? What have you learned so far? So I'm going to paste this in. And what we learned so far around the word pi, there's definitely a big topic about universities. There's a topic about number theory. And there's an interesting topic here. Anybody know what this is about? Yeah, there's some nice historian there. There was an emperor in China whose last name was Pai. And there's even this one. If you remember, there's a Pi movie, which is another cool movie that might be on my list of things that I like. And since this is a dynamic graph, we can load more data. So here's, you can add any word, and if you come to the demo, you can, to our booth, you can say what words you want to add. Here I'm just going to add the word graph, since it's supporting our community here. And so what we're doing is taking the same graph out there and just adding more documents, which corresponds to adding more vertices and more edges associated with these words. And originally, we had added 4,000 documents, which had, 139,000 words, which led to about 2 million edges. So that's 2 million edges in the graph. And now we have about 3.7 million edges. And we can call the same function and see how the topics have changed. So remember, before we just had the word pi. Now we have the word documents with the word pi and with the word graph, and now we can see we discovered a topic about graphs. There's other topics. There should be one here about social networking, which social, if it hasn't come up yet, it comes up as it starts iterating over the data. And you will see if you come to the demo here, this one here is emerging about data, networking, and other things from the topics related to graphs. So here we are. This is what you should expect from GraphLab 3. So I'm going to just stop it and just close off the talk. Thanks, Rajat, for fixing that. So, creating ideas of GraphLab on one machine, just GraphG or GraphLab in the cloud, so you can either run it on a single machine or single workstation, or you can run a cloud-based system, reading your files from HDFS or other related file systems. You can use Yarn or MPI. There's lots of possibilities here. And on top of it, we have a runtime which uses the Warp engine and has a distributed data structure that lives over time, which is abstracted away in the C++ library, which on top of it has our toolkits that you know and love, so things like social network analysis, collaborative filtering, recommender systems, and beyond. And it also adds new ETL tools and Python and Java bindings, which allow us to do things like the interactive console that I showed you. So this is what you should expect to see. And since we have the ability to support more usability, and the idea to do things like Python consoles and other languages and make it easy to try it out and use it on your own system, we can also help you support your participation. And we're doing that by moving to GitHub. So you should get GraphLab from GitHub from now on. We're going to provide new toolkits, so you should see a demo today of the Cloud CV toolkit that some folks have implemented in the context of computer vision. And we're going to have continued engagement through the open source community. And so we're using that to do the community development and to inform the development of GraphLab. So the most important thing for us is to get your feedback and help us decide where we're going. Where should we go? What should we do next? What's important to you? And if you find somebody with this shirt today, please come and tell them what you care about and what's important to you and what you need. And another way of doing this that would be very helpful for us to define the future of GraphLab and to help for you to influence us is for you to go and do our survey, which just asks for some ideas. It only takes a couple minutes. If you go to graphlab.org/survey, or we have some Chromebooks in the back there near our stand where you can fill in and tell us what you want to see in the future versions of GraphLab. And just for extra motivation, you can win an iPad, you can win a Chromebook, or you can win a Kindle, depending on what kind of technology you're most excited about. And on top of this, you might ask how to engage, so you can engage the open source community. But we're also selecting a set of strategic partners. And some of you are already in our strategic partner group, but we want to do about a dozen engagements in the coming months, where that will help define where we're going and hopefully will help provide value to your company. So if you're interested in that, you can reach us at partners at graphlab.com. We'll work together to make GraphLab viable in your system for your needs and use that to fall back and provide more value for the version that we use with the community and with everyone else. So if you're excited, just reach us there. And let me just take 30 seconds here to close by saying that beyond making GraphLab more usable, what I'm most excited about in the future GraphLab is bringing usability to machine learning. I want to build that Cadillac for machine learning. Because this is an exciting time to do machine learning. This is a time where we have tons and tons of data, and the surprising thing is that people expect machine learning to work. When they pick up their phone and they use Siri, they expect that to recognize what they want. And I find that incredibly valuable and incredibly exciting because it provides me with a unique opportunity to, and us here, for a unique opportunity to change how we deal with data. But the problem is that today, pretty much every system, every deployed system of machine learning required a bunch of PhDs to make that system work. And that's not what we want in the future. So the goal of the GraphLab project is to make sure that huge-scale machine learning can be accessible to everyone. And I hope you'll work with us to make that possible. So if GraphLab 1 was about possibility and GraphLab 2 was about scalability, we're excited to talk about GraphLab 3, which is the usability focus. So come to our booth and tell us more about what you hope for. Thank you.